Patty Simpson with Simpson Math. In this video, we're going to look at how the normal distribution is used in everyday life. So here we have an example of some data that when it's collected, it forms a normal distribution. IQ test scores follow a normal distribution. Remember this notation, this means that it's a normal curve. This is the mean of my data. So the mean of an IQ test is 100 and the standard deviation is 15. So remember with our notation that we do our mean and then our standard deviation. We want to know what is the probability that if a random person is pulled off the street, their IQ is greater than 100. Well, first, I'm just going to draw this curve that we have there. We know that it's a normal curve. So on my number line here, I'm going to put in the middle my mean. And then the standard deviation tells me the distance from the mean. I'm just going to count by that distance. So if I go up one standard deviation from the mean, I'm at 115. That 15 is the distance of the standard deviation. So that's one standard deviation above the mean. If I go up another standard deviation, I'm at 130. And one last standard deviation, and I'm at 145. I'm going to go backwards. So subtract 15 from 100, and we're at 85. Subtract another 15 from 100, and you're at 70. Subtract one more standard deviation, and you're at 55. And then I'm going to draw the normal curve. Remember that the mean, median, and mode are here, so that's going to be our largest point there. And then the normal curve is symmetric. We've looked at that in a previous video. So we have our inflection points here, and they're symmetric, so these two dots would fold and meet. And then again, at that second standard deviation and at the third standard deviation, we have some symmetry. And then we just connect our dots into the curve so that it's, we have that change in concavity there at that inflection point. And remember then it has this asymptotic behavior where it never quite reaches the line. It's just getting closer and closer there as we go. Okay, so there is my normal curve with my mean of 100 and my standard deviation of 15. And I want to know what's the probability that I get someone that's 100 or greater. And remember that probability and area are related. So if I can just find the area under the curve here from 100 on, then I'll be able to tell us the probability. Well, the area for the whole thing is 100%, and I'm just taking and cutting this in half, and this half is the same as that half. So that tells me that the probability that I get someone greater than 100 is 50%. So then this probability that I get someone with a test score of greater than 115. Well, let's look at that area then. So 115 is here at one standard deviation above the mean. And I want to know the area under the curve here from 115 on. So we're going to use our empirical rule to help us determine this. Remember, with the empirical rule, we can look at that within one standard deviation is 68% of the curve, or the area under the curve is 0.68. Then within two standard deviations from the mean is 95% of our data. So randomly, if I were to choose a person off the street, 68% of the population then would have an IQ, or I would expect that probability that I'd get somebody between an IQ of 85 and 115 would be 68%. The probability I get someone with an IQ between 70 and 130 is 95%. And then the probability I get someone from 55, 3 standard deviations out, to 145, well, that's 99.7% of our population has an IQ between 55 and 145. So it's really rare to be on the outsides of that. And we want to know, well, what's the probability that I have over 115, that a person that we randomly choose is over 115 IQ. Well, we know that this part, you just told me, was 50% from here on up. And I know from here to here is 68%. Well, I want to do this 50% minus this little sliver. And that little sliver is half of this 68%, or 34%. So to find this probability, I can take my 50%, that's from 100 on, and subtract off that 34%, which gives me a 16% probability, or the area under the curve there is 16.16. So there is the chance that I get over 115. Let's try now greater than 85. So now I'm looking at this area, so from 85 on, that direction. And again, I'm going to use that same strategy where if I can use this half of my graph, I'm going to notice that 50% is that way, so the probability is going to be more than 50%. And what I've added to that is half of this 68. So I've added to it this other 34%, half of that 68. So here I've got 50% plus 34%, which gives me 84%. So the probability I get someone with an IQ greater than 85 is 84%. Let's look at an IQ of less than 70. So now I'm going to look at this IQ of less than 70. Let's undo the area under the curve here for the rest of it, so that we're just looking at this part that is under 70. And let's see what we can use to help us out. So there are actually several different ways that we could do it. One way would be to say, well, let's use that same strategy where I'm looking at 50%, because from here on is 50, and then I want to subtract off half of the 95%. So half of 95 would be 47.5%. From here to there would be 47.5. I could take that 50% and subtract that off. Another way to do it would be to take and say, well, I know from here to here is 95%. So on the edges, if the whole thing makes up 100%, on the edges is 100 minus that 95, which gives me 5%. Subtract, I need only half of that, so I end up with 2.5%. So there's several different ways to do it. You could do 100% minus 95% to get the 5% on both ends, and then divide the 5% by 2 to get 2.5%. Or you could take and say, well, 50% of it minus the 47.5% of it also gives me that 2.5%. Either way, we expect for 2.5% of the time to get a person with an IQ of less than 70. If we look at 130, that is similar. So notice that that's on the other end. So this half, this piece, and this piece are equal to one another because this is symmetric. So this is also 2.5%. Now, I taught in public education for many years, kindergarten through high school, and I actually saw this number being used in the school system and this idea of normal being used. So one way that you could get into special ed was if your IQ was less than 70. Then you were admitted into special ed. And you can see where that 70 comes from. We expect 2.5% of the population to have an IQ of less than that. So that is kind of rare. So if your IQ was under that, then you were placed in special ed. On the flip side, when you were tested for GT, if your IQ was above 130, then you were placed into GT. So those requirements, you can see at the time that I was teaching, I didn't think, where did they get the numbers from, until I started teaching math, and I realized that 70 IQ and that 130 IQ, the reason they chose those is because those are 2 standard deviations away from the mean. When the testing started, at least here in Texas, at first school districts were maneuvering to make sure that students got into special ed so they didn't have to take the test. And the state came along and said, hey, now there are too many people in special ed, so let's stop that practice. And they again used this normal when they were deciding on making their policies. So they decided that only 2.5% of the population in a school should be categorized as special ed. And they based that 2.5% off of this normal model. So the normal curve is used in daily use constantly, whether you realize it or not. Math Made Simple, it's Simpson Math. Thanks for watching.